Okay, hello everyone, welcome. And today we are going to talk about stacks and queues. But before that, maybe just a check-in question, like what would be your next travel destination? Anything that you have planned or you wish to go in near future? Any place that you're longing to? So you just put that in the chat. And if you are belonging to one of the courses, then also for the extra credit, please put your year-end program. Sarah, would you like to introduce our group?
Hey everyone, we're WIT, as I think everyone here knows. Our aim is to just provide an empowering experience for folks. Actually, what I want to plug right now is if you're interested in applying for WIT eBoard, our applications are open. You can look for that in the CS student mailing list. We've been sending it out almost every week. The application closes April 15th. So yeah, if you're interested, let me know. We can talk. But that's what's coming up for us right now.
That's nice. And today we'll start with stacks and queues. I think you've already done that in your course in the semester, so it would be an easy topic for you to grasp. So stacks, what do you mean by stacks? So it's a data structure where you have, you can imagine like a pile of books where on the top you put the book and the one to go out would also be the one that was put last. As in you cannot remove the red book before you remove yellow book, and you cannot remove yellow book before you remove the blue book. So the first one to go in the stack would be the red one, but the first one to go out would be the one on the top, which is the green one. So it's like a data structure like this, where the top one is the one on the top, and then you push and pop in a stack like fashion. Any questions? Okay, so how do you implement a stack? There are two ways. So anybody knows or anybody wants to just talk about it before we move? Like how is this internally put into the data structures? How is it implemented?
It follows first come, first serve, right?
Yeah. No, I think stack is last come.
Oh, sorry. LIFO, last come, first. So,
Yeah.
Okay. LIFO, yeah. So we can push from top and that it will going to take out from bottom.
Yeah. So if you had to implement a structure like this, which data structure would you use? Maybe an array list or linked list?
Yes.
So if we have to go by linked list, how would your implementation be? You can just draw it together. So basically your stack is something where you have element number 1, then say you have push of element 2, then you have 3, 4, and then once you remove, you have the 4 coming out first, then you have 3 coming out, 2 coming out, and 1 coming out. And your linked list is nothing but you have nodes which are connected with a next node, and there is one pointer which is the head to it, right? We have nodes connected in this fashion, and the last node is null. So if you want to implement a data structure like this with the help of linked list, say you have the first push to 1, then maybe you can create a node with 1 and tell that this is the first head. But now when you have 2, now how would you incorporate 2 to create a stack? Like how would you just put 2? So there are two options. Either you put 2 in the end over here, or you put 2 in the beginning, and then so one option is this. You make the 1 point to 2, and the other option is you put 2 in the starting and then make 1 next and then null. So here in the second option, this is A and this is option B. The head would be the new node that you added. So like with 2 nodes, it's not really good to appreciate, but say if you have a more third node, then in the first approach, you add it in the end. And for the list, you always have the head pointer. So in order to put it towards the end, you would have to start from the head. You have to keep iterating it and then remove it and then put it in the end, right? So the insertion would be order of n over here. But in the second approach, if you want to just put it in the head, you always have the access of the head. So you can just create a new node, make the new node's next pointer to the current head, and update the current head to be the new node. So here you don't have to iterate how many elements are there in the list. You can just do it in order of 1. So in this approach, if you try to put it towards the end, it would be order of n. And if you just put it in the beginning, it would be order of 1. So which one is better over here? Which one would you go for?
I just want to check with the group. Have you all started talking about stacks yet? Yes. Okay, good. Just want to make sure that we have like the background information for that.
So given an option, would you like to iterate over the list and then keep on adding towards the end? Or you would like to just have it in the beginning of the list and update the head pointer? Do you see any pros and cons for both approach, or both are similar in your view?
Values are different.
Yeah, so So if you have to iterate toward the head, starting from head, you would have 1, 2, 3 over here. And if you have to go over here, it would be 3, 2, 1. And what would be the order for the stack for removal? Last in, first out. So whatever goes in last comes out first. So it would be 3, 2, 1. Also, this time complexity is order of n for the first approach, and for the second one is order of 1. So 1 is always lesser, and which is better. So it makes sense to use it in a way in a linked list where you put it in the start and then remove it also from the start. Yeah, makes sense. And the second way is by array list, where in the array, as in you have the indexes like 0, 1, 2, and so on and so forth. And then you keep on adding elements from like say 0 index, then 1 index, then 2 index, and also keep a pointer called top, which will always point to the top element, like the one which is last filled, so that once you have to remove, you just remove it from the top and decrement the pointer for top. Once top becomes 0 or goes to -1, then you know that the stack is empty in that case. And for the linked list, if your head is null, that means the list is empty.
This is definitely one of the cases where I think the linked list implementation has a lot less overhead and is a lot easier to implement. So if you haven't implemented a stack yet before in your classes, try the linked list one first before you try the array implementation.
Yeah, that's true. So list would be much more simpler, but yeah, the only drawback in that case is you have to have a next pointer everywhere. And also, like we reviewed in the linked list, that the elements are not put contiguous in the memory. So in that way, you would not even have the benefit of caching. Like you cannot have all the elements put in the cache together. So yeah, like in the implementation wise, it's easier to see, but in the terms of complexity of the memory of machine, it makes sense to more use it in the array. Yeah. So then we have just seen like how to put one stack in an array, but it is also possible to have two stacks where you put two simultaneously in one array, where for the stack 1, you start it with 0 and keep on incrementing with index 0, 1, 2, 3, and also maintain top 1 for stack 1. And for the second stack, you start it with n and keep on decrementing it, where you have n, n-1, n-2. The other stack is going from 16, 23, 42, and so on and so forth. So the top 2 will have the pointer to stack 2. So for top 1, when you pop out, you'll remove say 99, then 15, then 8, which will be last in, first out for it. And for the stack 2, it would be removing 42, 23, 16, which will be again last in, first out. So you can have two stacks together in one array as well.
Why might you do that?
Just to save on the memory. So if you have to put two stacks in two different ones, then for array, you have to initialize it beforehand, the total number of elements you have in the array. So if you put like 100 elements, then you are already using up that space. And even if your stack never grows up to 100 elements and say it is nearly about 50 or 25, then you have the rest of the memory wasted. So in order to optimize it on the memory front, you can put either two stacks, or it's also possible to have multiple stacks in the same. But the problem with that is the overflow situation. Like once the stack in between is, so for multiple stacks, one you start from the beginning, the second you start from the end, and third you start somewhere in the midpoint. And once you start filling the elements of the middle array or whichever array it is, and it bumps into the next array, you probably have to shift all the elements which is here back to the element which is free. So put like a middle point in between the two empty locations and try to shift it there. So you'll have space again in the end to add more elements into the stack third and stack second. So you can have multiple stacks as well, but this is just optimizing in terms of memory. And the next structure is queue. Queue, you can imagine like a queue waiting for movie tickets or something, where you have first element, the first person who comes in the queue would be served first, and the last one will be served last. So it's like this structure where the tail means the first one which entered earliest point of time, which would be dequeued first, and then enqueuing would be one which happened latest, like nearest to now, and which would be like a head pointer. So you need two pointers, head and tail, in order to represent a queue. So this is also called like FIFO, first in, first out. And stack was LIFO, where it's last in, first out. Any questions on this? So again, with queues, you have two implementations, like basic data structures, similar to stacks, where you have linked list and arrays. For linked list implementation, okay, let's go again. So you have queue with say 1, 2, 3. The push happens in the order of 1, 2, 3. So the pop will also be in the order of 1, 2, 3. The first one to be pushed was 1. So the first one to be popped out would also be 1. Then the second one pushed was 2. So maybe the tail goes over here and the head still remains here. Then the third to push was 3. So the tail increments by 1. Say 4 comes in. So your tail 4 would be added towards the end and the tail would increment by 1. Make sense? And say pop happens after it. So whenever pop happens, the head pointer increments by 1. So 1 is outputted and the head is over here. Then again pop happens, then 2 is outputted and head comes over here. So again, there are two implementations. One is linked list, where you create one node for each element that is pushed. Like say 1 is pushed initially, then head and tail both are at 1. And 2 is pushed. So your tail pointer moves ahead. On push, it's the tail pointer that moves ahead. And on pop, it's the head pointer that moves ahead. So on push of 2, the tail moves to here. Then push of 3, tail moves to here. Push of 4, say tail moves to here. And then say pop happens. So pop will print the element which is at the head 1 and move the head pointer ahead. Then next pop will also print the element 2 and make the head pointer ahead. So what would be like the head and tail, say if I have a push 5 or push 6 and then a pop? How would this work in this? So what happens when push 5 happens?
So 5 would go to the end of 4.
Hmm.
And then 6 would go after that.
Okay, and which pointers would be changed?
Oh yeah, the tail would change. First change to 5 and then
Okay.
change to 6.
Hmm.
And I think 1 gets popped after and the head changes to 2.
Head is currently at 3. We had already 1 and 2.
Okay. Yeah, then 3 gets popped and head changes to 4.
Okay, yeah. So basically that's how you implement in a linked list fashion. So you don't have once you have popped the head pointers, you don't have access to them and they get out of the queue. And your queue is in between head to tail always. So head is here and tail is here. So your queue is this much only right now. Make sense? And for the array implementation, it's a little bit tricky because again, say, okay, let's have a fresh start. So in array, you always have to pre-specify the memory, as I said. So say you have a memory of 10. So how many total elements can you have inside this array? You can have is 10, right? So 0 to 9 would be the last one. So now if you have push similar as last time, you have 4 elements which are pushed together, say 1, 2, 3, 4. And then you pop, so the tail would be here and the head would be here. Now, once you pop the element over here, say 1 is popped and head moves ahead. And say you push 5, 6 in the end, like we did last time. So tail is here and you pop one more element. So 2 comes here and head comes here. Now you have to, your currently queue is in between head and tail, which is from 3, 4, 5, 6, these elements. But, and you have more capacity to put till 9, say you put 7, 8, 9, 10. But now you want to put 11. So your list does not have a capacity to add 11 in the end. But there is space here in the starting to add 11 and 12, since those are not part of the list now. So in order to like have 11 to go in the starting, if there is space available, you imagine this queue, this array as a circular queue. So you can put 11 and 12 over here. So your queue would be from 3 to 12. So that fits in the array only if you have a circular fashion like this. So in order to put it as an array implementation, you have your array in terms of a circle. So once it ends, and if there is space in the starting, you can start it in the beginning. It's a little tricky. Any questions for this?
Yeah, it's been a while since I've covered the circular implementation. Is there, like, do you have to leave parts of it empty? I remember something like that. Like, do you have to leave one space empty, or can you really fill out all parts of the array?
You can fill out all parts of the array. Yeah.
Okay. I think maybe I saw an implementation that did that. Like that had like almost like a dummy head, kind of like a linked list.
Okay.
And then Mia asked a question, how do you know if the beginning of the array is available?
Oh, that's a good question. So yeah, let's look at it closely a little bit. So when you start, initially your head pointer is -1 because it's not yet started, and tail pointer is somewhere in 0. So the position where you are planning to start writing elements. So let's make this thing again. So your head is initially -1 and tail is where you are trying to put your elements. And let us take the size as 5 so that we can easily see elements which are empty. Instead of 10, we are now having the size as 5 only. So your head is somewhere here, which is out of bounds right now. And your tail is at 0. Now push happens for 1, so tail increments. Then push happens for 2, so you put where it is, tail is pointing and increment the tail. Push again happens at the start, at the last element. So now when, and say pop happens over here, where the head is again moved to the first element. So 1 is popped and this is empty. Head is 1. So your condition to check whether there are empty elements in the array would be where tail would be equal to head plus 1 plus tail would be equal to head. So if this condition is satisfied, then you know that there are no more elements in the array. So your tail say becomes 4 over here, then 5 over here, and then there is still space, you know, because your head is at 0. So yeah, you have to also check for the capacity. So you do a modulo n. Modulo would give you a remainder. So if your elements are 5, your tail is at 4, 0, 1, 2, 3, 4, and 4 plus 1 would be 5. And 5% 5 would be 0. So if 0 element is over here where your head is currently there, so yeah, this element is available over here. So check 1 plus tail, percentage of the size of the array, and compare it with the head pointer. Make sense, Mia? Yeah, okay. Yeah, so just like taking a summary of all the data structures that we saw in the time complexity. So for stacks, it is last in first out, and for queues, it is first in first out. And all the push pop, checking whether the top element is there or not, or is empty, happens in order of 1.
I have a question about the previous thing we were going over. So how do you make the end of the array point to the beginning?
Yeah, so you do just normally plus 1 and then take a modulo of n. So that will give you a remainder. So say you have 15 elements over here. 15 plus 1 would be 16. And 16% 16 would be the remainder when you divide 16 by 16, which would be 0.
Oh, okay.
Plus 1 would be 17, and 17 modulo 16 would be 1.
Oh, okay.
Yeah. Also, like there are a data structure called graph, which is still not introduced to you, but once it would be there would be 2 approaches to make the traversal of graph, which would be a depth first search where you go deep inside the layers first, and one would be breadth first search where you just check on the level it is first. And it uses stacks and queues heavily. So we are not going into the details, but just wanted to briefly touch upon the use case of stacks and queues. So maybe this is a very good use case where you have graphs to use depth first search and breadth first search as stacks and queues. And maybe you can have this as a takeaway assignment for today, where you implement a stack using 2 queues and implement a queue using 2 stacks. So it's a lead code problem. And if you have questions, then just post it on the Algo's Slack channel. But it would be a good assignment to do. So the first would be to just implement stack using a linked list, an array list, and then try to do it with 2 queues. And similarly, queue also, the first would be just a normal linked list, an array, and then 2 stacks. So 3 implementations for each, making it 6 implementations. And today we'll solve these 3 problems on lead code. The first one is a valid parenthesis. So the question says you have different sort of brackets, like a round bracket, a curly braces, and a square bracket. And you have to say whether a particular string which is given to you is a valid string or not. Like you have an opening and closing matching the tags where it is. So this is also a valid because opening of each type of bracket is before its closing bracket. But this is not valid because you don't have a closing bracket for round and you don't have an opening bracket for a square. So how would you do it? Any approaches? A hint is you can use stack data structure over here. So how will you identify if the opening bracket of any closing type is encountered before it or not? A simple way would be just iterate to all the elements before it and see whether it's there or not. So maybe I'll just draw it again on the sketch pad. Yeah. So maybe just imagine a stack like this. And for every element that you have, for the closing element, you see whether it's already pushed into the stack or not, whether it's on the top available or not. So for example, you have this, which is the opening brackets are always pushed into the stack. And when you try to see a closing, you see it's of a similar type, then you just pop it and say yes. So this is empty. So this makes it a valid string. The second one could be you push all the elements which is opening, and so you push the opening round, a closing round is encountered. So you pop the element and see it's an opening of the same type. So then it's a valid. Then you push the square. The next element is closing of square, and you try to pop the element from the stack, which is also valid. And then the third is a curly brace, and you pop it and see it's the similar type. Okay, let's take one example which is not valid. So you push round over here, and then while popping, you see that it's not a round but a angular bracket. So you see that it's a difference, and that's when you know it's not a valid string. Should we any questions on this? So how about if there is a string like this, open, close, and then say it's also curly braces, and then one more curly braces. How would the stack look like for this particular input? Anyone?
So I guess at first it gets the curly bracket, then it gets like I forgot what you call it,
Round.
the round one, and then the square one. And when it sees the other type, I mean the one facing the other way, it pops the square one first, then it pops the round one, and then the curly one. And then it also, after that, it adds the next curly one, and then it pops that one.
Okay. Yeah, that sounds really a good solution. And say what if there was a square bracket in the end?
Then I guess it adds the square bracket, but because it's not popped, and I guess the stack contains something after the whole string, you can you can return false or something.
Yeah, so this is also a good terminating condition. That's right. So at the end, you also have to check whether your stack is empty or not. So even if you encountered all the correct matches, but your stack is not empty in the end, then it might be wrong. And say what happens if your input is something like this, where there is a round bracket and you still don't have anything in the stack. So it begins with a closing tag, and you are trying to find something in the stack, but stack doesn't have it.
In that case, you would just return false.
Yeah. So you also have to check for the condition that the stack is not empty in that point of time before you try to pop. Yeah. Should we try to code it? Okay. So anybody would like to help me? First is we'll just create our stack that we had. And yeah, maybe I'll ask you to help. So what would be the data structure that goes in the stack? Should we put an integer or a character, or what?
Character.
Okay. So this way you create a new stack. This implementation is already given in Java utils, so you don't have to bother creating your own stack every time. You can just use the implementation from Java. So once you have the stack, you can just iterate for all the characters in the string. So an easy way to get the characters would be for character C from s.to char array. So this will give me in the first iteration, say opening bracket, then a closing bracket, and so on and so forth. So then what should I do in the condition to check?
You can take if loop. Then you can check character C is equal to opening bracket.
Which one?
Yeah, the round one. Yeah. Then you can put maybe, no, you cannot put semicolon, right? You can put the equal sign, right? Or you can put compare sign.
Here?
Yeah.
What should I do?
Comparison. No.
So for character, you can do comparison with directly equal because it would compare key values.
Yeah. You can push the bracket, right?
Yeah.
Yeah.
Otherwise?
Return false.
Here itself. So this will return false if the starting round bracket is not encountered. So if I have this round bracket over here, it will just return false if it encounters a closing round bracket. Yeah, so if it is a closing round bracket, then what should we do? As we discussed, we'll just pop out the top elements or check the top element, whether it's matching to the closing tag, the opening tag, then it's a true condition. If there's some different value or the stack is empty, then it's a false condition.
Okay.
If you see C is a closing bracket, then you check the top of the stack. So if stack is empty, first you check whether it's empty or not. If it is empty, then you know that it's not possible because you still haven't pushed anything. So you can just return false in this case. But if not, then you just check the top element. If stack dot, there's a function called peek, which will just not remove, but just see which is the top element. So it has not yet removed, it's just checking which is the top element. So if it matches the the same type of bracket. So it's a true condition, and then you just say stack.pop. And if it is any other type of bracket, which means if it goes to the else only if there is a square bracket or a round bracket. So if it has one of these two brackets in the top, then it goes to the else part, and then you can just return false. Make sense? Yeah. So else if this, sorry. Yeah, or the other could be, I can just copy paste from here. The other case is where it's the opening bracket but of curly brace. And if it is a closing curly brace, you check whether the top is an opening bracket. If not, the else part will go. The else part will go for the other two types of brackets, and you return false. And if it matches, then it's still in your criteria, and you continue the loop. Similarly, for the last sort of bracket, square one, you check whether it's opening and matching are same. And it goes to the else part only if it is a round bracket or a curly brace, and you return false. And as we saw that there was a case where we also had to check when it completes all the elements, your stack should be empty. So then you also check if your stack is empty. Then you return true, else you return false. Any questions on this? So we have our stack initialized to have characters inside it, and we put characters like opening brackets, any sort of opening brackets we have, we push it onto our stack. If not, then it's a closing bracket. And for each of the closing bracket, we see first whether the stack is empty or not. If it is empty, it means that our condition is not right, our string is not right. So we return false at that moment only. But if it's there, and if it is of some other type, then we return false. And if it's of the same type, we just remove it from the stack. And towards the end, we check whether the stack is empty or not. So if we try to do it for the sample cases, it works. And if we try for the case that we had also seen, where you have a curly braces, say a square inside it and a round inside it, that also works. A good way could be also, I think, to print the stack if that's possible. So let us just see system.out. I'm not sure if this would work, but if it works, then we can also see. Yeah, so here, just putting this statement, you can see at each iteration how the stack is. So for the first one, say it starts with a curly brace. So your first stack has a curly brace only inside it. The first character is a curly brace. Then the next element is a square bracket. So your stack has a curly brace and a square bracket. Then you have a round added towards the end. Then closing round will check whether the top element is also a same type. It is, so it will pop that element. Then closing square will check if the top element is the same type. It is, so it will pop. Then the round curly braces will also sit similar, so it will pop. And then opening is added, and then the similar type is closed. So if you add just a closing bracket, so it will just complete at the first step only. So none of the other steps would be done. So none of the other is checked because at the start only it completes. And say you have one additional over here, then it will check here whether the stack is full or not, and it will return false. So at the end, the stack has one element, so it is not empty, and it returns a false. Yeah, makes sense. Let's try to submit it. And yeah, it works. It says output limit exceeded because we are printing the stack every time. And yeah. Because you're printing the stack every time, it also takes some time to put it onto the output buffer, and it was giving output time limit exceeded, but now it works. Any question on this? What would be the space and time complexity? How big can my stack grow in worst case? Say if I have a stack, if I have an input like this.
Divya responded n over 2.
Okay, so yeah, so then that would be order of n, which is also like in the space-time complexity, you say n. And how many, so that would be for space or for time, Divya?
Oh yeah, for space, it would be n, but I think also for time, it would be n.
Yeah, why do you say for time would be n?
Because it iterates over the whole string that you give it, so it will check each thing.
Yeah, for none of the characters, you are checking it twice. Only once you are considering it, and there's just one for loop. So yeah, so we have order of n solution. Any questions before we move to the next one? Okay, if not, the second one, this one is based on Q. The question is number of recent calls. So you have a recent counter, this class, which counts the number of recent requests within a certain time frame. You have to implement this class such that the recent counter will initialize the counter with 0 recent request. So then your counter would be 0 over here. Initially the counter is 0. And then there is a method called ping, which is this. And it adds a new request at time t, where t represents some time in milliseconds, and returns the number of requests that has happened in the past 3000 milliseconds. So specifically, you have to just return how many elements are there in between t minus 3000 and the current time, whichever is passed in the pinging moment. So an example here they have given is you initialize your recent counter, then ping at first time, you ping at 1, then you ping at 100 time, then you ping at time 3001, and then you ping at time 3002. So when you ping at time 1, there's just one element in your, which has been pinged in last 3000 seconds. Then when 100 happens, so in last 3000 seconds, there's 1 and 100, so 2. Then in 3001, in last 3000 seconds, there's 100 and 3000, so 3. And then if you check for 3002, in last 3000 seconds, it would be like from 2 to 3002. So in this range, there is just 3 elements, 100, 3001, and 3002. So again, 3. So at every ping, you have to just return the counter which happens in the last 3000 seconds. Is the question clear? Makes sense? So
I'm actually not clear. When does it ping? What are like, when like, with how many times does it ping? Like, how do you know? What are like the constraints for each ping?
Oh yeah, sure. We can see the constraints. How do I stop this? Okay. Yeah, the constraints are here. So your time would be 10 to power 9, 1 to 10 to power 9, which is the individual milliseconds numbers that you have. And each case will be strictly increasing. So your time could have 1 to it will keep on increasing. It will never decrease. And at most 10 to power 4 calls would be made. So here you have 4 elements, but at max there could be 10 to power 4 elements.
Oh, I guess, yeah, my question was more like, when does a ping happen? Or
a ping happens when you got an input called ping, and when input called ping, the ping method will be called.
Oh, okay.
This would be input dependent. So yeah, you can just add in your like ping, and just say at what time it was pinged. So say for 4000 time, say 4001 time. You can keep on increasing like your pings and any time which is in between 10 to power 9. So you can have also a ping at 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, you can have so many pings. So like I've given you a hint that you have to use the queue data structure, but how would you identify like any time which is after 3000, you don't have to consider 3000 seconds old, you don't have to consider it. Let's look at the example again. So you start with an empty queue. You have 1 coming in over when your first ping happens. Then second ping happens at 100. So it's still okay. The next ping comes at 3001. So you have to consider 3000 seconds less from it. So which means you have to consider 1 to 3001, right? So which is 1 is still in the range. So you keep it. The next element you have is 3002. So now your range only will be 2 to 3002. 2 to 3002. Because you have to consider only the last 3000 elements from t minus 3000 to t. So when you put in 3002, you check whether there are any elements before 2, which happens because your range is only 2 to 3002. And the elements which are before 2, it's guaranteed that it would be in the beginning of the queue since it is in increasing order. And for the queue, you have first in, first out. So element which is first inputted would be removed first. So you just remove the 1 from it. Make sense? Then say you have a ping at 4000. So you add 1 more element called 4000 over here. And your range would be now from 4000 minus 3000, which is 1000, to 4000. So is there any element less than 1000 in my queue? Yes. My starting of the queue is less than that. So I'll just remove it and pop the element. So my answer would be then 3 elements are there. And similarly for 4001, I'll check whether is there any element less than 1001. So there are no elements. So now my answer would be 4. So every time the size of the queue where the last element that you evict is 3000 less than the current time, it remains in the queue. Make sense?
It does, but I have a question about that. So what would the output look like for the other case we made, the other one?
Yeah, so initially when you have 1, it would be just 1 element. Then when you have 100, you have 2 elements. Then you have 3001, so you have still 3 elements. Then for 3002, instead of 4 elements, because you have evicted 1, so you are left with 3 elements. For 4000, you are again evicting 1000. So instead of 4 elements, you are still left at 3. Then for 4001, you don't remove anything, so you have 4. And for 1 million, you have 5. So I think your answer would be 1, 2, 3, 3, 3. The total number of elements that are remaining in the queue would be your answer.
Would you have 5 or would you have 1 for the last one?
For the last one, oh yeah, because yeah, you would just remove all the elements which is before it. So yeah, it would be 1. Good catch. Yeah. So for the last one, you'll check which is like 999990, 9970, something like this. And any element which is lesser than this, you'll remove from the queue. So all these elements would be lesser, and so it would be removed from the queue. Yeah. Should we start the coding for this?
We only have 3 minutes left.
Yeah.
If people want to stick around, we can totally do that. And then if folks want to leave, I do have the attendance for today. So if you want to stay, feel free to. And I have the attendance down there. I just missed it.
Okay. Yeah. So you have your queue initialized, similar to Stack. There is an implementation in Java available where you initialize the queue with similarly a linked list. Normally that you have. And during the ping, what happens is you add to your ping the timestamp that you got. So your queue would be having queue.add the time. So for 1, you add 1, then 100, you add 100. You keep on adding the time. And at the same time, you also check whichever is less than 3000 of that timestamp. So in previous is say 3000, t minus 3000. So all the previous ones which are lesser than that, you keep on removing. So check while your queue is not empty. And your queue stop, which is peak, the first element in your queue, is say it is lesser than your previous. Then you just remove it from the queue. So for removing, the method is called poll. And then you just return the queue size. So here you are just checking how many previous elements you have to remove, all the ones which are lesser than 3000. And then you check whether it's empty. And the last element is lesser than the one that you have to keep. Then you remove it. And then your answer will be just the size of the queue. I have to use the variable full. Yeah, so this is what we had expected as well. For the example test case, obviously it's a subset, so it would work. Yeah, so it works. Any question on this code? Okay, yeah, then I'll be sharing the slides, and also there are some more lead code problems on this, so feel free to go through them. Thank you so much.
Thank you, everyone.